In the 1960s, a grand planetary tour to study the outer planets was proposed. It was an ambitious plan to send unmanned probes to the outer planets of the outer solar system. The grand tour could exploit a rare, unusual, and favorable alignment of the planets Jupiter, Saturn, Uranus, Neptune, and Pluto. This planetary alignment would occur in the late 1970s and would not occur again for 176 years. So the twin Voyager spacecrafts 1 and 2 were launched in 1977 to take advantage of this special planetary alignment. It would allow a probe to be sent to Jupiter and use that planet as a gravitational slingshot to extend the trajectory to the other planets further out in the solar system. The primary mission of the Voyager spacecrafts was the exploration of Jupiter and Saturn. After making a series of outstanding discoveries, the mission was extended. Voyager 2 went on to explore Uranus and Neptune, and is still the only spacecraft to have visited those outer planets. Remote control programming was used to endow the Voyagers with greater capabilities than they had when they left the Earth. Eventually, Voyager 1 and Voyager 2 explored all the giant outer planets of our solar system, 48 of their moons, and the unique system of rings and magnetic fields that those planets possess. In December 1977, Voyager 2 entered the asteroid belt. 9 days later, Voyager 1, traveling at a greater speed, overtook Voyager 2. In February 1998, Voyager 1 passed Pioneer 10 to become the most distant human-made object in outer space. In 2002, Voyager 1 left the solar system, rising above the ecliptic plane at an angle of 35 degrees and at a speed of 39,000 miles per hour. Voyager 2 also left the solar system, diving below the ecliptic plane at an angle of 48 degrees and a speed of 34,500 miles per hour. Voyager 2 still holds the record of traveling to more planets than any other man-made object in history. And Voyager 1 holds the record as the explorer from Earth that has traveled farthest from home. Voyager 1 and 2 completed their exploration of the outer planets in the first dozen years of their mission. Having completed their primary mission in 1989, the Voyagers were ready to begin exploring outside the solar system. In January 1990, with Voyager's new destinations outside the solar system, the project's designation was changed to Voyager Interstellar Mission. Both Voyagers continue exploring where nothing from Earth has flown before. In order to explore the solar system and beyond, Voyager 1 and Voyager 2 were equipped with a large number of special scientific instruments, suites, and subsystems. Most of the instruments are located on the body of the spacecraft. Each spacecraft is comprised of 65,000 individual parts. Of the dozens of working instruments that the Voyagers left Earth with, there are only 4 instruments still working on Voyager 1 and 5 instruments still working on Voyager 2. The low-energy charged particle detector and its 3 sets of particle sensors measure how many low-energy particles hit it and determine the speed of those particles. It studies cosmic radiation and particles that emanate from the Sun, the planets, and interstellar space. It is active on both Voyager 1 and Voyager 2. The Cosmic Ray Instrument looks for very high energetic particles from the Sun and other galactic sources. It currently is detecting the abundance of particles from inside the bubble of our Sun's influence, and also particles that dominate outside of the bubble in interstellar space. These readings help scientists determine when Voyager 1 entered interstellar space. It is still active on both Voyager 1 and Voyager 2. The plasma wave subsystem uses the 2 long antennas on the spacecraft, which stretch at right angles to one another. It was used to measure the electrical field components of plasma waves at the outer planets, but now the instrument is providing information about the changes to plasma waves as they enter interstellar space. It is still active on both Voyager 1 and Voyager 2. The magnetometer's job was to investigate the magnetic fields of the outer planets, but now its primary job is to search for the transition region between the interplanetary and interstellar media. They investigate the magnetic characteristics of the transition region at the solar wind boundary, where the Sun's magnetic influence interacts with and gives way to the magnetic field of interstellar space. This instrument is still working on both Voyager 1 and Voyager 2. Finally, the Plasma Science instrument looks for the lowest energy particles in plasma. It also has the ability to look for particles moving at particular speeds and, to a limited extent, to determine the direction from which they come. This is important as the spacecraft enters interstellar space. The instrument is now active only on Voyager 2. The other instruments have either stopped working on their own or have been shut down to preserve power. NASA has also systematically shut down heaters on both crafts to save power. In 1998, 21 years after launch, non-essential instruments were permanently shut off. The power source on each spacecraft is a group of 3 radioisotope thermoelectric generators. The RTGs give off heat by the decay of radioactive plutonium-238 and turning it into electricity. Eventually, the plutonium-238 will have decayed completely and will no longer be able to provide power, at which time all instrumentation will cease to operate. This should occur around 2025, but with careful power management, the Voyager team hopes to keep both spacecraft functioning through 2027, the 50th anniversary of their launch. The Voyagers are each equipped with a pair of thrusters, which are not used for propelling the craft forward, but for reorienting the probe so that its antenna is always pointing at the Earth. Otherwise, we would not be able to communicate with it. These thrusters fire in tiny pulses or puffs, lasting mere milliseconds, to subtly rotate the spacecraft so that its antenna points at the Earth. Since the primary thrusters on Voyager 1 had degraded, scientists fired up the backup thrusters in November 2017 so that Voyager 1 could keep its lock on the Earth. They had not been activated in almost 40 years, but they came to life to reorient the spacecraft's antenna. Voyager 2, whose primary thrusters were still working, was able to also keep its orientation toward the Earth. The Voyagers communicate with Earth via a 3.7-meter diameter high-gain antenna, which sends and receives radio waves via 3 Deep Space Network stations on the Earth. Voyager's main transmitter radiates about 20 watts, which is comparable to a typical refrigerator light bulb. By the time Voyager's signal reaches Earth, its strength has diminished to about 20 billion times weaker than a digital watch battery. Your iPhone has 100,000 times more memory than the Voyager spacecraft. Although state-of-the-art at the time, Voyager's computer systems are vintage 1974-75, causing NASA to look for programmers who understand decades-old software. In fact, Voyager is equipped with an 8-track tape recorder, which it uses to store information for transmission to Earth. In 1978, the transmitter failed on Voyager 2, so the backup transmitter has been used ever since. The Voyager's signal, however, is bright when compared to most natural objects studied by radio telescopes. NASA's Jet Propulsion Laboratory communicates with Voyager practically every day via NASA's Deep Space Network, but it takes someone with 1970s design experience to be able to understand Voyager. The Deep Space Network consists of 3 antenna complexes that are stationed around the globe approximately 120 longitudinal degrees apart. They are located in Madrid, Spain, Goldstone, California, and Canberra, Australia. The global separation of the stations allows the spacecraft to have an uninterrupted line of sight with at least one station regardless of the time of day. These massive antennas have been upgraded several times to accommodate receiving signals from Voyager and other spacecraft. Voyager 1 and Voyager 2 signals can still be received by all three stations, but Canberra is the only one with a powerful enough transmitter that can transmit to the Voyagers. Centers at each DSN site receive incoming information, then send it to the Spaceflight Operations Facility at the Jet Propulsion Laboratory in Pasadena, California. Due to the incredible weakness of the spacecraft's downlink, by the time it reaches Earth, large parabolic reflectors and hyperbolic subreflectors collect the microwave radiation and focus it on a cryogenically cooled receiver at the base of the antenna. While one of the antennas is more than powerful enough to transmit to Voyager, a single 34-meter antenna does not collect enough electromagnetic radiation to detect Voyager's downlink. So antennas at each site are linked together so that they can simultaneously receive the signals from the spacecraft, providing increased gain. It currently takes more than 19 hours for Voyager to receive signals from Earth, and 19 hours for Earth to receive signals sent by Voyager. The massive antennas that comprise NASA's Deep Space Network will pick up a faint, distant signal for the final time around 2025. It will track the downlink signal from the spacecraft as it sputters into silence and becomes part of the background noise of the solar system, never to be heard from by humans again. So how do we know Voyager 1 is in interstellar space? The most convenient way to determine the location of Voyager 1 was to measure the temperature, pressure, and density of plasma, or ionized gas, around the spacecraft. Everything inside the solar bubble or heliosphere should be exposed to plasma that streams from the Sun, whereas interstellar space is filled with denser plasma emanating from interstellar space as a result of the explosion of giant stars millions of years before. Unfortunately, Voyager 1's plasma detector stopped working in 1980 and hasn't functioned for almost 40 years. So scientists needed to examine the plasma or charged particles which fill the bubble encasing our solar system and compare that with the plasma or charged particles that occur in interstellar space without the use of Voyager 1's plasma detector. We needed to compare the solar wind versus the galactic wind, each traveling in a different direction. Since July of 2012, the solar wind has decreased and the galactic wind has increased, placing the craft in what is known as the magnetic highway. Plasma consists of charged particles and is more prevalent in the extreme cold of interstellar space than in the bubble of solar wind that permeates our solar system. The plasma detector on Voyager 1 had been designed to measure the composition of those two plasmas, but without that instrument, such measurements were not possible. Fortunately, and by chance, a pair of solar flares blasted charged particles in Voyager's direction in 2011 and 2012. It took a year for the particles to reach the spacecraft, but they did, eventually, and they provided sound wave information that could be used to determine how dense the plasma was in Voyager's location. When that blast wave reached Voyager, it caused the plasma around Voyager to vibrate or oscillate in a certain particular tone. By measuring that sound wave, we could measure the density of the plasma surrounding the spacecraft. Scientists knew then that Voyager 1 was in a place no spacecraft had ever been before. It was on the magnetic highway, where all particles that were inside the heliosphere had streamed away and were now gone. What we now saw instead were cosmic rays from outside the heliosphere. The data showed a huge spike in the number of galactic cosmic rays from outside the solar system, and a corresponding decrease in particles emanating from the Sun. All of the pink-colored ions you see here were from the hot bubble of solar wind coming from our Sun and permeating our solar system. They were leaving the heliosphere along the magnetic highway, and at the same time, the blue ions seen here are the cosmic ions moving at a higher speed, coming in from interstellar space and from a different direction. Voyager 1 is now in a region where it is surrounded only by cosmic rays accelerated from elsewhere in the galaxy. Many scientists now declare that Voyager 1 is in interstellar space. There is a caveat that comes with Voyager 1's exit from the solar system, however. Many scientists consider the term solar system to mean not only the planets in our solar system and the sun's influence beyond, but that the solar system extends up to the edge of the Oort cloud. If so, it will take another 300 years for Voyager 1 to reach the inner edge of the vast Oort cloud. And the journey through the Oort cloud could take another 30,000 years. Only then will Voyager 1 be considered to be in pristine interstellar space. Voyager 1 is currently traveling at about 38,000 miles per hour, 1,000,000 miles per day, or about 1,000,000,000 miles every 3 years. That velocity will never change. It will go on forever. Having left the solar system, the next time it will encounter a star is in 40,000 years, when it flies about 1.7 light-years away from an obscure star in the constellation Camelopardalis, called AC plus 793888. It will be in the year 40,282 AD. In 56,000 years, Voyager 1 will pass out of the Oort cloud. After another 570,000 years, Voyager 1 will brush past the stars GJ 686 and GJ 678. Voyager 2, traveling at 34,500 miles per hour, is also on course to enter interstellar space, likely late 2019 or 2020. Voyager 2 is heading out of the solar system in another direction from Voyager 1. Voyager 2 is not headed for any particular star, but in about 61,000 years from now, Voyager 2 will pass out of the Oort cloud. After 296,000 years, in the year 298,000 AD, Voyager will pass by the star Sirius at a distance of 4.3 light-years. About 100,000 years after that, Voyager 2 will brush past two stars, Delta Pav and GJ 754. Beyond this, both Voyagers will continue into the void, passing through dust clouds and local bubbles of empty space, blown upon by dying stars. The spacecrafts could be affected by dust clouds and the gravitational pull of rogue, starless planets, however. Ultimately, like the stars in the Milky Way, the Voyagers will orbit the center of the Milky Way galaxy. It will take 225 million years to complete one orbit around the center of the Milky Way, and the Voyagers will orbit for billions of years, or until our neighboring galaxy Andromeda collides with the Milky Way. Due to the enormous distances between the stars, it is likely that the Voyagers will survive this collision of galaxies, however, and continue their journey. Frozen in the vacuum of space, both spacecraft and their contents need not fear decay. The ultimate death of the Voyagers could come from thousands of micrometeorite impacts or one unforeseen collision. The Voyagers, however, will probably outlive the solar system long after our sun dies, and long after the Milky Way galaxy has been unalterably changed or disappeared. The Voyagers are destined, perhaps for all eternity, to wander the cosmos, carrying with them the only traces of our human existence.